Hi everybody. This video begins chapter 10, which is called the Laplace transform. The Laplace transform is a very special transformation that is actually going to give us a brand new technique for how to solve initial value problems. So we're beginning with section 10.1, which is going to be starting with just the definition of the Laplace transform. Okay, so in order for me to define this, I need to give you guys a fact from calculus that you may or may not remember, that the limit as x goes to infinity of e to the negative ax is actually equal to 0 for any a bigger than 0. Okay? Okay, why? Because this really becomes 1 over e to the ax, and of course if a is a positive number, 1 over infinity tends to 0. Okay? So this is an important fact that we have to remember. And this leads us to our definition. So let's let f be a function defined on an interval zero to infinity. Okay. The Laplace transform, and this is what we're defining, so the Laplace transform of f is the function capital F of s defined by, so here's capital F of s, okay? The way that we define it is capital F of s is going to be the integral from 0 to infinity of e to the negative st times f of t dt, wherever it converges. Okay. Now, just so that you guys remember, there is something you should recall, and this is from Calculus 2. You need to remember what it means to have 0 to infinity, right? How do you integrate something from 0 to infinity just from calculus? Remember, this is the same as taking a limit as, let me give you a new letter here. Limit as r goes to infinity of the integral from 0 to r f of x dx. Okay, so this is true. This is how you learned how to integrate up to infinity in calculus. Okay? Now, important to note, before I move on to the next page here, it's important to note that this really is a function of s. Even though you see a t in here, that t is going to go away after you solve the integral because this is a definite integral, right? When you have a definite integral, the variable that you're integrating with respect to is never going to appear in your answer. S is different though because you're not integrating with respect to s, so in the end all you're going to have are s's left. That's why this is a function of s. Okay? So this is important here that this function f appears in here. All right? That's why we call it the Laplace transform of the function f. So what changes is not the other part of the integral, but just that double underlined part right there. Different for every function. Okay? So let's go on to some notation. We denote the Laplace transform of f by, this is what it looks like. Laplace transform of f. This is how we write it. Okay? So note, this is important, not all functions have a Laplace transform, okay? Since the limit above must converge. Well, let me not say above. How about the limit in the definition must converge? Okay, so this is important. You have to first check to see where it converges. So let's do, what I want to do in this next example is let's find the Laplace transform of some basic functions, okay? So example. Find the Laplace transform L of f of the following functions. So let's start with part A. What if we just have the function f of t is equal to 1? What's the Laplace transform of 1? So the Laplace transform of 1 is, let's write the definition down. It's the integral from 0 to infinity of e to the negative st times 1. So it's just going to be that integral. Okay? And we know that that's equal to the limit. Let's go ahead and use a capital N for this. We just need a new dummy variable. Limit is capital N goes to infinity of 0 to capital N of e to the negative st dt. So what's this equal to? This is the limit as capital N goes to infinity of. So what would the integral of e to the st with respect to t be? This is going to be 1 over s e to the st, and we're going from t equals 0 to t equals capital N. So this ends up being oh, I just realized I made a mistake. Somehow my negative sign disappeared. There's a negative here, which actually means that this should be negative 1 over s e to the negative st, right? And so this is equal to the limit as, you know what, I can even pull the negative 1 over s behind the limit because it's got no n's in it, right? So I've got this, and then I've got e to the negative. Remember, I'm plugging in t values, so e to the negative sn minus, and if I plug in 0, I get 1. So what happens as n goes to infinity? This guy right here goes to 0. And so what does this limit become? It becomes 1 over s. Now remember, because I made that limit go to 0, this is only going to be true if s is positive, okay? So here's how we would write the conclusion. The Laplace transform of 1 is equal to 1 over s for s being positive, right? Because anytime s is 0 or negative, this limit would not have even converged, so we would get nothing, right? So this is how we would write the answer of the Laplace transform of 1. Okay, that was part A. Let's try another one. So for part B, let's figure out the Laplace transform of just the following function. How about f of t equals t? So the Laplace transform of t is going to be the integral from 0 to infinity of e to the negative st times t dt, which, as we know, if I want to write that using limits, it looks like this. Okay. Let me go ahead and figure out what this integral is. I'm going to do the indefinite integral on the side. So this is going to be an integration by parts integral. So we're going to let u equal t, du is dt, dv be e to the negative st dt, and v is equal to negative 1 over s e to the negative st. So then this guy is equal to uv, so that's negative t over s e to the negative st, minus the integral, so plus 1 over s integral of e to the negative st dt. Okay, but then I get another 1 over s that comes out of the integral, so it becomes negative 1 over s squared. So this guy becomes negative t over s e to the negative st minus 1 over s squared e to the negative st. Okay, so this is what I get for my antiderivative, right? Okay, so let's see what happens. So this is going to equal the limit as n goes to infinity of, I'm going to plug in capital N into that integral, so I get negative n over s e to the negative ns minus 1 over s squared e to the negative ns. All of that minus, and then I'm going to plug in 0. If I plug in 0, I get 0 minus 1 over s squared. So I'm doing the limit as all of this goes to 0, okay? So what do we end up with here? Well, remember, what we actually get if we do this guy clearly goes to 0, right? Now what about this guy over here? This guy's actually going to go to 0 also. Now, what about this limit, okay? This limit is actually 0 as well, and this is actually because of L'Hopital's rule, okay? This is because when you try to take a limit as x goes to infinity of x over e to the x, you get infinity over infinity, and the exponential always dominates after using L'Hopital's rule, right? So this will go to 0, okay? So these two go to 0, and in fact, we end up with our limit equaling 1 over s squared. So think about what we have learned. Example 1 says that, oh, another thing to notice too is that this is true for s being positive, right? We assumed that when we took these limits up here, okay? Now, there is something that we have learned, okay? If we do the Laplace transform of 1, we get 1 over s for s positive. If we do L of t, we get 1 over s squared, where s is positive. So we see a pattern starting to emerge, and actually what we can do is do the Laplace transform of t to the n. Now, without me running through the whole thing, it's not that hard to prove. You actually end up with n factorial over s to the n plus 1, where s is positive, okay? This is a really useful formula, so I'll put a box around it, okay? The n factorial comes from when you actually do this integral. That's what's going to happen when you do the integration by parts multiple times here, okay? All right, so that's good. We now have a way to do the Laplace transform of any power. Let's keep going. How does the Laplace transform react to exponentials? So what if we have e to the at where a is a constant. So a constant, okay? So what would be the Laplace of e to the at? Okay, this is going to equal the integral from 0 to infinity of e to the negative st e to the at dt. So what is this equal to? Well, this is just e to the t times a minus s, right, if you combine exponents. So let's do the limit as n goes to infinity of 0 to n. And we're doing e to the t a minus s dt. Okay, so how would we do the antiderivative of e to the t times a minus s? Well, we're going to end up dividing by a minus s. Okay, so that ends up being, I keep dropping, oh no, we're good. Yes, there we go. Okay, so what would be the antiderivative here, right? We're going to do a minus s, and we divide by that. So this is equal to 1 over a minus s, and then limit as n goes to infinity of, this would be e to the t times a minus s, but we're going from t equals 0 to t equals n. So that's the antiderivative, right? So if we plug in t equals n, we end up with one over a minus s times e to the n times a minus s minus, and if we plug in 0, it's just 1. Okay. So what would this limit go to? Well, if n goes to infinity, then we know that this is, so let me show you guys what this guy is right here. This is really e to the, if I pull out a negative, then this becomes s minus a. So this actually goes to 0 as long as s is larger than a. So let me go ahead and say that this goes to 0. And so the negative and the negative make it become 1 over s minus a as long as s is larger than a. And so this is what we have. This is what we've learned. Okay, so we're getting these interesting functions of s by taking the Laplace transform of exponentials of all sorts of functions, right? Part D, I'm not going to work this out in detail, but I will give you guys 2 more formulas. What would be the Laplace transform of cosine of something? Okay. If you do the Laplace transform of cosine, so when you work out the integral, you actually get s over s squared plus b squared, and that's for s being positive. And when you do it with sine, you actually end up with b over s squared plus b squared, where s is positive. So we now know the Laplace transform of some basic functions. I want to talk about some linearity properties of the transform as well. So first, an important property is that the Laplace transform of a function plus another function is actually going to be the Laplace transform of f plus the Laplace transform of g. Okay? Why is this? Well, this has to do with when you're actually calculating this integral. Of course, if you do an integral like this, this is going to equal e to the negative STF plus e to the negative STG. Okay? That's just by rule of integrals distributing over addition, right? It is also true that if you take the Laplace transform of any constant times a function, the constant actually pulls out. Why? Because constants pull out of integrals, right? So what do these two facts tell us? It tells us that the Laplace transform is a linear transformation. Okay, very cool, right? So we now know that the Laplace transform actually operates linearly, and it takes functions to other functions, and this is a linear transformation. Okay. So let's do an example where we apply this principle to a problem which is actually the sum of some Laplace, the sum of functions whose Laplace transforms we know. So I want us to find the Laplace transform of f, where f of t is equal to 4e to the 3t plus 2 sine of 5t minus 7t cubed. Okay? So what would the Laplace of f be? Well, by linearity, isn't this equal to 4 times the Laplace of e to the 3t plus 2 times the Laplace transform of sine of 5t minus 7 times the Laplace transform of t cubed. So what would this be? So first, the Laplace transform of e to the 3t. So that means that 3 is our a in the old formula. So this would be 4 times 1 over s minus 3 plus 2 times, remember for sine our formula was you take 5 and you divide it by s squared plus 5 squared. So 5 over s squared plus 5 squared. And then minus 7 times, what's the Laplace transform of t cubed? Well then 3 is our n in the formula, so this would be 3 factorial. So let me write it this way. 3 factorial over s to the 3 plus 1. What does s have to be larger than? Okay, well, in this one, s has to be larger than 3. And in this one, s has to be larger than 0. And for the last one, s has to be larger than 0. And so this means that they're all true if s is larger than 3. So our formula is going to be, or I should say it this way, the Laplace transform of f then is going to equal 4 over s minus 3 plus 10 over s squared plus 25. And then you have 7 times 6, so that's minus 42 over s to the 4th power. And s is bigger than 3. This would be our answer. Okay. So linearity is extremely important because we can now do it with complicated stuff. However, I want to start to demonstrate that you can even do the Laplace transform of piecewise functions. So let me define what it means to be piecewise continuous, because we're going to be using that phrase a lot in this chapter. A function f is called piecewise continuous. on an interval AB, if we can divide AB into a finite number of subintervals, such that 1, f is continuous on each subinterval, and 2, f approaches a finite limit as the endpoints of each subinterval is approached from within. Okay. So this is part of the definition, okay? If f is piecewise continuous on every interval of the form 0b, where b is a constant, then you can say f is piecewise continuous on 0 to infinity. Okay, so there are a couple of things we're mentioning here. All of this is what it means. So all of this is what it means for f to be piecewise continuous from a to b. But then we're saying if from 0 to any number it's piecewise continuous, then we say that f is piecewise continuous on 0 to infinity, okay? So that's what this last part is defining, what that means. So piecewise continuous, I want to draw a little picture of something that looks like a piecewise continuous function. Something like this. If you were to continue on this pattern forever, this is an example of what a piecewise continuous thing might look like. It's saying that even though we jump around, they all have a finite limit, right? There's no vertical asymptotes here. It's never going to infinity. And there's only a finite number of discontinuities each time. So you always approach one end, and the limits are well defined and finite on each end. Okay? All right, let me just write an example here. The function f defined by f of t is equal to t squared plus 1, 2 minus t, and 1. These are the conditions So this function that I just defined right here, this guy is piecewise continuous. On 0 to 3. Right? Because it satisfies all the conditions. The conditions are, it's continuous on each subinterval, certainly this is, and f approaches a finite limit as the endpoints of each subinterval is approached from within. None of these go to infinity, none of these mini functions inside, right? None of them go to blow up at infinity at any number. So this is piecewise continuous. Let's actually practice finding the Laplace transform of a piecewise continuous function. Okay, so let's do a really basic one here. So example, let's define f to be t when it's between 0 and 1 and negative t when it's bigger than 1. Let's find the Laplace transform of f. Now, it seems like this would be a difficult thing to do. How do you calculate an integral for a piecewise function? Well, let me show you that it's really not that bad, okay? So remember, the definition, it goes from 0 to infinity of e to the negative st and then f of t dt. Now, of course, the problem with f of t is it's different depending on where we are. However, what we're going to do is we're going to break it up into two pieces, from 0 to 1, and then plus from 1 to infinity. And the reason we do that is from 0 to 1, I'm going to use this for f, and from past 1, we're going to use this. So this is what it's going to look like then. I guess since it's a negative t, I can pull the negative out, and I'm going to get that, right? So what would this become? Well, I've already done this antiderivative earlier, right? This is just going to be, now remember, this guy right here is the limit as capital N goes to infinity of the integral from 1 to n of t e to the negative st dt. Okay, so we have already done this antiderivative on the last page. So remember, this is just going to be negative t over s e to the negative st minus 1 over s squared e to the negative st. And so it's the same antiderivative for both. The first one, it's going from 0 to 1. And then the next one, if I do plus, I just can flip the order here. So I'm going to do the limit as n goes to infinity again, and I'm going to do from n to 1, right? So it's going to be negative t over s e to the negative st minus 1 over s squared e to the negative st, and I'm going from n to 1. Okay, so this is what I'm going to have. This limit's only going to apply to that to that last guy when we plug in n, right? So here's what we get, right? We have negative 1 over s e to the negative s minus 1 over s squared e to the negative s minus, then I plug in 0, I get 0 minus 1 over s squared. So all of that plus, if I plug in 1, I'm going to get the exact same term again as I did over there. And then finally, if I plug in n, I end up with minus, oh no, let me write it over here, plus I have limit as n goes to infinity, and this is going to be negative n over s e to the negative ns minus 1 over s squared e to the negative ns. Okay? Now, when I apply this limit, I want you to see what happens, right? This goes to 0 and this goes to 0, right? Because, again, the exponential on the denominator dominates the numerator, okay? So what happens to the rest? Well, this and this are the exact same term, but they get added together, so there's two of them. And then you also have a positive 1 over s squared there, okay? So how would I write this answer? I would write it like this. This is going to equal, so, well, actually, let me write this on, yeah, this is fine. So the Laplace transform of f is going to equal 1 over s squared, and then I'll just write it this way. I'll pull out a negative, why not? So I'll pull out a negative and I'll write 2 times 1 over s e to the negative s plus 1 over s squared e to the negative s. Okay? So what assumption did I make? Of course, I made the assumption that s was positive when I took these two limits to 0, and so this is only if s is greater than 0. So there you go. That's my answer. So pretty interesting that you can apply it to piecewise functions, but you can do this, okay? Thanks a lot, guys, for checking out this video. Hopefully it was helpful.